Okay, so this is our second video on sketching polynomial graphs, and we want to, in the previous video we looked at polynomial graphs. So when I say polynomial graphs, we're just going to focus initially really on cubics and quartics. So in the last video we looked at cubics of this form, okay, and we know that if a is bigger than 0, that's going to give us a cubic graph that's going to be this shape with its point of inflection at hk, because it's translated to the right by h and up by k, and it's going to go up as we go from left to right. If a is a negative number, we know that that's going to have reflected the graph in the x-axis, and so it's going to go, the shape will go down as we go from left to right with its turning point still at hk. We also looked at quartics, y equals a times x, sorry, I wrote squared up there, sorry, so that's the cubic. And we also looked at the quartic, and it's x minus h to the power of 4 plus k, and we know that if a is bigger than 0, it will be the basic quartic shape, translated to the right by h and up by k, so the quartic having that sort of square-bottomed parabola. Look, sorry, it shouldn't be kind of veering off out there. And if a is negative, our graph will have been reflected, so it's going to go up this way, it's that same sort of flat-bottomed quartic shape, and turning point will still be at hk. Okay, so those are the graphs that we dealt with. In doing that, we have to obviously find x-intercepts and y-intercepts. Calculating x-intercepts when our equation is in this form is really easy, because both these equations can be just solved by rearrangement. Subtract k, divide by a, take the cube or the fourth root, and add h. Okay, so what we want to look at today is, and what we want to understand is, unlike parabolas, where every single parabola can be written in turning point form, every single quadratic equation can be written in turning point form, every single quadratic equation looks like a parabola, always. Cubics and quartics and higher degree polynomials, there's much more variation of what can start to happen. Okay, so if we can write a cubic equation in this form, it will take this shape that we looked at last lesson. If we can write a quartic function in this form, it will take this shape that we looked at last lesson. However, not all cubics and quartics can be written in that form, and if they can't, they're going to look different. Okay, and what we want to focus on today is the other kinds of cubics and quartics. Okay, so not eliminating the fact that we can have cubics and quartics that look like these, we can also now introduce that we can have cubics and quartics that might look like these. There are a couple of other variations that are possible too, but we won't really worry about those for now. So generally speaking, a cubic, so a parabola, a quadratic function has at most one turning point. The graph turns once. A cubic function can have at most 2 turning points. Technically, they can have 2 turning points or 1 point of inflection. They're the only options. Okay, you can have, we've only focused on cubics with stationary points of inflection. It is possible to get a point of inflection that's not stationary, but we're not going to worry about those. Okay. The key thing then to decide is whether you have a positive x cubed term, and that if you were to expand it all out, is it going to be positive x cubed, positive 2x cubed, positive 1x cubed, positive 17x cubed? Is it going to be positive? In which case, if it is, you'll find that the graph goes up as you go from left to right. Okay, so the graph starts down at the bottom and finishes up. Okay, if it's got a negative x cubed term, it goes down as you go left to right. It starts at the top and finishes at the bottom. You can liken to that to what you know about linear functions, because they're actually the simplest possible odd degree polynomial. So a linear function, you know, if you have a positive x term, it will go up as you go from left to right. If you have a negative x term, it will go down as you go from left to right. Okay, so you can apply that same logic to the cubic. Positive leading term when it's an odd degree polynomial, the function will start at the bottom and go up as you go from left to right. Okay, there'll be some bends along the way, but it'll start down and finish up. Okay, negative leading term in an odd degree polynomial will start at the top and finish down. So if it was a degree 5 polynomial, it can have at most 4 turning points, and it could do that. But it would, if it had positive x to the power of 5, it would start at the bottom and finish at the top. Whereas if it was negative x to the power of 5, sorry, negative, with other terms afterwards obviously, it would start at the top and have 4 turning points and finish down. Okay. So odd degree polynomials, positive leading term up as we go left to right, negative leading term down as we go left to right. Okay. Quartics are like, we can think about parabolas. Okay, so when we have y equals positive x squared, we know our parabola is happy. When we have y equals negative x squared, we know our parabola is sad. Same logic extends to the quartic. Okay, when it's positive x to the power of 4, if we can write it in the form we did last lesson, we get that shape. We could also have at most 3 turning points, or we could actually have 1 point of inflection and 1 turning point. Okay. Regardless, the positive x to the power of 4 term means the graph starts up, finishes up, starts up, finishes up, starts up, finishes up. Okay. If, however, sorry, I'm going to add that, leave that other shape in there. If, however, you've got a negative x to the power of 4 term, the graph will start down and finish down. Okay, so whether that is going to be this shape that we looked at last lesson, okay, the sort of square, sorry, it's not a very good quartic, but anyway, you know what I mean, the sort of square bottomed, or square topped in this case, quartic. But if it's negative y equals negative x to the power of 4 when you expand it all out, it's going to, or negative 2x to the power of 4, or whatever, it's going to start at the bottom and finish at the bottom. And that would be true of all even degree polynomials. If you have a positive leading term in an even degree polynomial, so if it was a degree 6 polynomial, it'd have 5 turning points, but if it was positive x to the power of 6, it would start up and finish up. If it was negative x to the power of 6, it would start down and finish down. Okay, so that's the first thing we want to decide. Okay, first of all, have I got a cubic or a quartic or a higher degree polynomial than that? Second of all, is it a positive cubic, in which case it'll go up as I go left from right, or a negative cubic, in which case it'll go down as I go left to right? Or is it a positive quartic, in which case it'll start up and finish up and other things will happen in between? Or is it a negative quartic, in which case it'll start down and finish down and other things will happen in between? Okay, the other thing that starts to happen is as we increase the number of bends and turning points, we're getting more x-intercepts. So when we were dealing with only these functions, because they're all in this form over here, if we find x-intercepts, we can solve those just by rearrangement. Subtract k, divide by a, take the cube or the fourth root, add h, and you've found your x-intercept or intercepts. These are going to be more complicated. Okay, cubic could have up to 3 x-intercepts. Okay, and in that case, if it's got 3 x-intercepts, we're probably going to have a cubic equation that we need to factorize and use the null factor law to find those. Similarly, a quartic could have up to 4 x-intercepts. Okay, and so finding the x-intercepts is going to be a bigger, of bigger importance here. Okay, in fact, in these graphs, finding the x-intercepts would be where we would begin, and from there we would think about what's happening with the graph shape. So let's talk a bit about just focusing on finding the x-intercepts first, and use that to think about what the graph is going to look like. Okay, so, and then we'll formalize this a bit more. So the first thing here is I identified that if I were to expand out all these brackets, I would have positive x cubed. So I've got a positive cubic, which means it's going to start at the bottom and it's going to finish at the top. Okay, it's not going to have endpoints, I'm not going to draw them, but just it's going to start down and finish up. Okay, so we already know that. We don't technically at this point know that it isn't this, although I do, because if I calculate my x-intercepts, so my x-intercepts are when I let y equal 0, so I'm solving x minus 1 times x plus 2 times x plus 5 equals 0, and this is nice and easy because it's already factorized for me, so I can straight away use my null factor law, which tells me that x minus 1 has to equal 0, so x could equal 1, or x plus 2 equals 0, so x could equal negative 2, or x plus 5 equals 0, so x could equal negative 5. Okay, so if we think about, we know it's going to be positive cubic, we know it's now got 3 x-intercepts, so there's the x-axis has to sit somewhere in here, and we know those x-intercepts are at negative 5, negative 2, and 1. So we've actually already pretty much got a good sense of what our graph looks like. Let's draw that better, let's make sure we sort of scale where those intercepts are a bit more accurately. Okay, so what do we want? Negative 5, negative 2, and 1. So let's put our x-axis over there. So 1, 2, 3, 4, 5. Okay, so we're going to have 1, -2, and -5. Okay, and so we're going to have, we know it's going to start down and finish up because it's a positive x cubed. Sorry. Now, at this point, we don't know where the turning points are. Now, I've drawn it so the turning point looks like it's the y-intercept. I don't know that. It's just a fluke of how I drew this particular graph. Please, I want you to be careful. I find often students really try really hard and they kind of bend the shape of their graph to make sure that the turning point happens there. There's no reason the turning point has to happen there. If it suits your graph for the turning point to happen somewhere else, that's fine. We don't know how to calculate the turning points, and for now, for this year, we won't be calculating the turning points. You can only do that if you've got your CAS. We can have a look at that down the track. Okay, so for now, we're just interested in getting the shape right in terms of the direction of it and getting the x-intercepts, and then we can also calculate our y-intercept. So let's label these and let's calculate the y-intercept, which we probably should have done before we drew it in, but that's okay. There's nothing else happening on the y-axis other than this y-intercept, so we just need to know how to label it. So y-intercept, we let x equal 0, so we're going to get -1 times +2 times +5. So -1 times +2 is -2 times +5 is -10. So this is going to be, this y-intercept, sorry, is -0, -10. Okay, let's have a think about this next one. So again, if we think about, if we were to expand this out, the leading term is going to come from when we do x times -x, so it would be -x cubed. There'd be other terms, obviously. But that means it tells us we're going to go down as we go from left to right. If we calculate our x-intercepts, we let y equal 0, and we have a factorized quadratic. So we know that either x is going to equal 0, or x plus 1 equals 0, which means x is -1, or 3 minus x is 0, which means x is 3. So we've got 3 x-intercepts, negative cubic. So again, for it to be a negative cubic with 3 x-intercepts, it has to have 2 turning points, and the x-axis is going to go somewhere through there, and we're going to have, you know, -1, 0, and 3. Okay, so again, let's be a bit more precise about that. Now, if one of the x-intercepts is 0, immediately we know the y-intercept is going to be 0. You can check if you want, but it'll be 0 times 1 times 3. So it's just going to be 0. Okay, so let's draw in a scale. -1, 1, 2, 3. So we know -1, 0, and 3. So again, your turning points don't need to be, they're not going to be symmetric about the x-axis. So this is going to be a much shorter one because it's got to turn around much more quickly to get back here. This is going to be much further away. Okay. Again, you don't know where they are, but just try and get that sense of getting that nice smooth cubic shape happening through there. Okay. So you're going to have -1, 0. Your x-intercept, your x and y-intercept is 0, 0, and then 3, 0. So we've got all intercepts marked. We don't need to mark turning points for now. We don't have the tools that we need to be able to do that. Sorry. Okay. Let's have a think about this one. So again, if we were to expand this out, it's going to be, from this bracket, we would get an x squared, and then we'd multiply that by x. So we're going to get positive x cubed. So it's definitely a cubic and a positive cubic. Okay, so we're going to go up as we go from left to right. Now, when we calculate the x-intercepts here, so we let y equal 0, we're going to get x minus 2 squared times x plus 3. So it's already factorized. So the only way those two things can multiply together to equal 0 is if x minus 2 is equal to 0, which means x equals 2, or if x plus 3 is equal to 0. Now, strictly speaking, you could say x minus 2 squared equals 0. Square rooting both sides means x minus 2 is 0, so x equals 2. You don't really need to worry about that first line. If x minus 2 squared is 0, then x minus 2 has to be 0. And we get x equals -3. All right, so y-intercept, we can work that out while we're here. Y is going to be -2 squared times +3, so that's 4 times 3, so it's going to be at 12. Okay, so let's think about this. We know we've got a positive cubic shape, just draw in a positive cubic shape, but it's only got 2 x-intercepts. So I want you to think about, before I tell you, what must be happening in order for there to be only 2 x-intercepts? Where does the x-axis have to be? We know if the x-axis is in here, we'll get 3 x-intercepts. So that's not going to be what's happening. So the only way we're going to get, hopefully you've worked out, the only way we're going to get two x-intercepts is if either the x-axis is here or the x-axis is here. Those are the two options. If we were looking at this top option, maybe I'll make one of them a different color so I can clearly tell you which one I'm talking about. If we were focused on the blue x-axis, if we were to put the x-axis there, we've got x-intercepts at -3 and +2. So this would have to be -3, 0, and this would have to be 2, 0. Okay. The other alternative is the black axis down the bottom here, which would mean this point here is -3, 0, or this point here is 2, 0. So then our question is, how do we know which of these two it's going to be? And there's a clue in what the original equation looks like. Okay, and the clue is this. So the fact that it's the x minus 2 bracket that is squared means that that's the x-intercept where we will have the squared behaviour, the turning point. The graph will look, it's not a parabola, I don't want to confuse things mathematically, but it will look a bit like a parabola shape at x equals 2. Whereas the second bracket, x plus 3, that's only got a power of 1, that's just a linear graph. That looks like a line when we're close to x equals -3. So your x-intercepts tell you, your factorized form of your equation tells you both about where the x-intercepts are, but also about what the graph shape looks like at those x-intercepts. So actually it is going to be this version of the equation. So let's draw that in. Okay, so what we know is we're going to have x-intercepts at +2 and -3, sorry, okay, so we've got intercept at 2 and intercept at -3. We know we've got a positive cubic, so it goes up as we go from left to right. We know at 2 we're going to have a turning point. So my graph's going to actually cut through the x-axis at x equals -3. It's going to touch or bounce at x equals 2. And that also fits with the fact we calculated our y-intercept to be +12. Alright, let's have a look at one more similar, and then we'll sort of start to formalize what we've seen in these examples. So this time we've got 4 minus x times x plus 1 all squared. Okay, if we were to expand out these brackets, you're going to have -x. The leading term is going to come from doing -x times x squared to give us -x cubed. So it's going to be negative cubic. Okay, so down as we go left to right. X-intercepts, we let y equals 0. We've got our nicely factorized cubic. Oops, sorry, it's a squared. So straight away we can use our null factor law. 4 minus x equals 0, so x is equal to 4 if I add x to both sides. X plus 1 equals 0, so x equals -1. And the fact that there is a squared here tells us that we've only got two x-intercepts again, so it has to, one of them has to be a turning point. The squared here tells us that that one will be the turning point. Okay, and there'll be another x-intercept at 4. Our y-intercept, let's calculate that. Y is going to be 4 times 1 squared, so that's just 4. Okay, so we've got -1, sorry, -1 and 4, so 2 x-intercepts. We know it's a negative cubic, so it's going this way. Okay, we know that we're going to have a turning point at that x-intercept at -1. So it's going to come down, it's going to turn at that x-intercept, it's going to go back up, and then it's going to cut through at this x-intercept. Again, I don't know how high this is, it doesn't matter. Focus on just trying to get that smooth cubic shape. Try not to, try and bend it to get it to do certain things. Just focus on getting the shape. Okay, so 4, 0, minus 1, 0, and our y-intercept is at 0, 4. Okay, so let's sort of formalize and extend a little bit what we're seeing here. So when we have our equation in a factorized form, we can easily establish not just where the x-intercepts are, but also the shape of the graph at that x-intercept. So when we have a linear factor, so x minus a with no power, okay, We learn from that x equals a is an x-intercept, and because it's linear degree 1 factor, or that factor is to the power of 1, the graph will just cut through the x-axis at that point. If we just focus close to the point, it'll sort of look a bit like a linear graph at that point, just cut straight through. Okay. If we've got a squared factor, we know that x minus b all squared tells us that x equals b is where there is an x-intercept, and the squared tells us that at that x-intercept we're going to get a turning point. Sometimes we say that the graph touches the x-axis or bounces on the x-axis. And I like to think about it, it's not technically, but if we were to just perhaps focus in very closely, we might be able to think about the fact that it's sort of like having a parabola shape at that x-intercept. So x-intercept is at b, we get a parabola shape at b, so we get a touch or a bounce. We can actually extend that logic further out. If when we factorize the polynomial, we actually have a cubic factor. So let's say, for example, you had x plus 1 times x minus 4 cubed. So you'd have x-intercepts at -1 and +4, and at +4 you'd get a cubic shape, okay, so a point of inflection at that point. And at this one you've just got a degree 1, so you'd just get a cut. So you'd have a graph that had an x-intercept at -1 and +4. It's a quartic, it's a positive quartic, it would cut here and it would have a point of inflection here, okay? And we can extend that out further. If it was a factor to the power of 4, so x minus d all to the power of 4, that would tell us that x equals d is where the x-intercept is, and that at that x-intercept our graph would behave like a quartic, so it would be a flatter turning point, okay? And we could extend that. If we had x minus e to the power of 5 as a factor, x equals e is where the x-intercept is, and you'll get at that x-intercept, at the point e0, you'll get behavior like a degree 5 polynomial. So it'll be that even flatter point of inflection. Okay, degree 6, degree 7, etc. We can extend that out. So when we have our polynomial in factorized form, we know immediately where the x-intercepts are and what shape the graph is making at those x-intercepts. And then we can put that together with the factor, whether it's an odd degree polynomial or an even degree polynomial, whether it starts at the bottom and finishes up, or starts up and finishes up, or whatever, okay? So let's do some sketching. Sketch graphs of each of the following clearly showing all intercepts. Okay, so when it's already factorized, we shouldn't need to write too much down. We can see straight away that our x-intercepts are going to be at x equals 0, x equals -3, or x equals 7. They're all degree 1, or all to the power of 1, those factors, and so at each of those x-intercepts the graph is going to cut through the x-axis. The y-intercept, nice and easy here because we've got this x-intercept at 0, so when you let x equals 0 you'll get 0 times 3 times -7, which is 0. Okay, we know it's a positive cubic, so the shape's going to go up as we go from left to right. Alright, so let's mark some points. -3, 0, 7. Positive as we go from left to right. Sorry, I hit the edge of the screen. Okay, again, you know, a bit like the parabolas, draw your shape in and then mark your x-intercepts if you need to, but you want to get that sense that your scale's sort of right. In fact, I've probably got it at 7 a bit far out, but that's okay. Alright, so there's my graph. All axis intercepts marked. So turning points for now, we don't know how to do. You won't learn how to do that till second semester of year 11. But all axis intercepts, x-intercepts, y-intercept. Okay, question 6. We want to sketch this cubic. Now, it's not in factorized form. It's not in this nice form. So the first thing we want to try and do is factorize it to see if we can find the x-intercepts and sketch it from there. So, I haven't given us much space here. I think perhaps I meant to have an x in there. Let me just have a quick look. What's coming? Oh no, okay. Right, small, we haven't got a lot of space. Okay, so we're going to need to factorize it. If it's not already factorized, we need to factorize it. So let's focus on, so essentially what we're doing is we're trying to find the x-intercepts. We know that to find the x-intercepts we need to solve 0 equals negative x cubed minus 3x squared plus 4, okay, which is the same as solving positive x cubed plus 3x squared minus 4, okay, so that's probably going to be easier for us to think about the factorising. So to solve that we need to factorise it because we can't just rearrange it, there's no common factors. So the first thing we do is try and find a factor. P of 1 plus 3 minus 4, good, that works, okay. So that tells us that x minus 1 is a factor. Then once we've got our first factor, we divide it in. So x minus 1, now I'm focusing on solving this, so this is the cubic I want in here, okay. So I've changed the negatives around. So x cubed, now remember if you're missing a term, which we're missing the x term here, we're going to include 0x, so that when we do our subtractions, we're subtracting like terms. Okay, and hopefully now we're getting pretty good at our division. What do we multiply x by to get x cubed? That's x squared. X squared times x is x cubed, x squared times negative 1 is negative x squared, and then we subtract. What do we multiply x by to get 4x squared? That's going to be 4x. Multiplying 4x, sorry, forgot to bring down the next term as well. 4x times x is 4x squared, 4x times minus 1 is minus 4x. Subtract. 0 minus minus 4 is 0 plus 4, so 4x. And then we bring down our next term and we repeat. What do we have to multiply x by to get 4x? Well, that's plus 4. 4 times x minus 1 is 4x minus 4. Good. That's what we expected. Okay, so now we're continuing from here. Now we know that our equation is x minus 1 times x squared plus 4x plus 4. And that is x minus 1, that's x plus 2 all squared. Okay, so from here we know that our x-intercepts are going to be x equals 1 and x equals negative 2, and at this point we're going to get a touch or a bounce because it's a squared factor. Okay, this one will just be a cut because it's a linear factor. So we've got our two x-intercepts. Our y-intercept is going to be easier to find by going back to the original equation, because when you let x equal 0, you're just going to get left with 4. Okay. And so we should have all the information that we need. So we're going to have negative 2 and 1. It's a negative cubic. Okay, so it goes down as we go from left to right. So it's going to come down. We're going to have the touch or the bounce at negative 2. It's going to come back up. I'll extend my x-axis, my y-axis in a bit. Actually, sorry. So we're going to come down, and we come back up, and then we're going to come through again here. Okay, so 1, 0, negative 2, 0 is my two x-intercepts. My y-intercept, we've calculated at 0, 4. Now again, my turning point looks like it's almost happening at the y-intercept. Purely accidental. Please don't bend your shape to make sure that it happens at the y-intercept. There's nothing to say the turning point will be the y-intercept. Okay, so that's that one. All right, let's have a think about a couple of higher degree polynomials. So degree 4 here, if we thought about expanding that out, you'd get an x squared from this bracket and an x squared from this bracket. So you get positive x to the power of 4. And then all sorts of other stuff. So it's going to be a positive quartic, which means it's going to start up and finish up. Okay, let's think about our x-intercepts. So we let y equal 0. So we're clearly going to get x equals negative 3, and the squared there tells us that we're going to get a touch or a turning point or a bounce at that point. And when x equals 3, we're again going to get another touch or a bounce. So we've got two x-intercepts, both of them have got turning points at those x-intercepts. Let's think about our y-intercept. So let's let x equal 0. So it's going to be 3 squared times negative 3 squared. So that's 9 times 9. So big y-intercept at 81. Alright, so let's think about what we've got here. We've got two x-intercepts. They're symmetric. And we're going to touch at both those points. So let's have there and there. Sorry, it's not very symmetric. Try again. Okay, so 3, 0 and negative 3, 0. It's a positive quartic, so we start up and finish up. Okay, so it's going to start up here, it's going to bounce, it's going to start up here, it's going to bounce here, it's going to come up here, it's going to have a big y-intercept. And actually in this case, because the x-intercepts are both symmetric about the y-axis, it will have its maximum turning point at that y-intercept. It's going to bounce again here, and it's going to finish up again because it's a positive quartic. Alright, so we've got that sense of what's happening. So we're going to start at the top, we're going to bounce or touch at the first x-intercept, we're going to have a big y-intercept, we're going to bounce or touch at the second intercept, and then we're going to keep going. Okay, so my y-intercept is 0, 81, my x-intercepts are labelled, my y-intercepts are labelled, and my shape is correct. Okay, last one, question 8. So again, if we think about expanding, we're going to have negative x times x cubed. So we're going to get negative x to the power of 4 if we were to expand that out. So it's a negative quartic this time, so it's going to go this way. Start down and finish down. If we think about our x-intercepts, we let y equal 0, 2 minus x times x minus 5, all cubed. Alright, so we're going to get 2 minus x equals 0, so x equals 2. We're going to get x minus 5 equals 0, so x equals 5. Now, this is power of 1 on this bracket, so the graph's just going to cut at this point. This is a power of 3 here, so we're going to get a point of inflection at this point. Okay, so let's have a think. We've got positive 2 and positive 5, so both positive. Well, let's calculate our y-intercept. I think it'll be a quite big positive y-intercept here. So y is going to be, we let x equal 0, so it's going to be 2 times negative 5 cubed. Sorry, it's a negative, big negative intercept, sorry. So that's 2 times negative 125. So that is negative 250. Okay, so that tells us sort of where to put our axes. We've got both positive x-intercepts but a big negative y-intercept. Actually, sorry. Just thinking through in my head what it's going to look like. Alright, so we're going to have 1, 2, 3, 4, 5. So 2 and 5. It's going to start down and finish down. Okay, so it's going to have quite a big negative y-intercept, so let's get that sense. We don't know exactly, sorry. It's going to cut through at that point, and it's going to have to turn around to come back to this x-intercept where there is a point of inflection, and then it's going to keep going down. So we've got our point of inflection at 5, 0, we've got our cut there at 2, 0, and we've got our big negative y-intercept at 0, negative 250. Alright, so the key is identify whether it's a positive or negative cubic or quartic, find your x-intercepts and think about the shape of the graph at those x-intercepts, and that should be enough to enable you to draw the graph, obviously also calculating your y-intercept and marking that on your graph as well. Okay, so the work today is on a worksheet, Sketching Polynomial Graphs Part 2.